Breaking the wall of concrete pollution. How green concrete can reduce the giant carbon footprint of construction. Franz-Josef Ulm, MIT.
On November 9th, my father called me. The wall fell. His voice broke into thousands of splinters.
Well, thank you very much for giving me a chance to spend this memorable day with you here. Well, my point today will be to give you the chance to have a quick speed dating with concrete and to see what's all about it. But I'm sure at that moment, looking here, the oranges which you see standing there, you may have only one question: what concrete and oranges have in common. So that's my assumption, my hypothesis, and I'm going to work through that with you in the next, well, how many minutes? 13 minutes and a few seconds. Well, what's the larger picture about it, what we are looking in today? In these times of economic crisis, we look into large-scale infrastructure renewal, particularly in the United States. People speak about a New Deal. The question we raise, will it be green? Green meaning here sustainable development. And sustainable development has three components which we should never lose out of sight. It includes economic growth. It includes social progress, impact, job creation, very important these days, and while reducing the environmental impact. As such, doing something here for materials and structures has an impact which has a cultural meaning, a social meaning, environmental meaning, and which can be transformational far beyond the immediate use of a project. Now let's put that in context about concrete consumption on this world. The data here shows you a list of worldwide consumption of materials, and you readily recognize that concrete, after water, is the material the most consumed on Earth. Everybody on this Earth, every person, consumes roughly 1 cubic meter of concrete every year. I don't know where you stand on 9th November 2009 with your yearly concrete consumption. You still have a few weeks to go to finish your cubic meter. But that's actually the impact of whatever we do to the material. Concrete, 25 billion tons produced. We could think about replacing it by wood, but already we bypassed largely the worldwide ecological capacity of Earth. Now, this immense consumption of concrete comes at a non-negligible environmental price. And that price results from the production of cement and the production which requires energy, but also releases in other forms CO2. In fact, each ton of cement produced roughly releases 1 ton of CO2 into the atmosphere. Just to give you a number, 1 ton of CO2 is the absorption of a tree over 100 years of lifetime. So roughly a column here in this building, 3 meters high, made out of concrete, is roughly 1 ton of cement. So if I made a rough calculation of the building with the concrete, and I came to something like 1,000 trees absorbing CO2 for 100 years, that's about the CO2 impact just by construction here of this building. Now, what are we looking at here in terms of Concrete Agenda 2050? Well, if we were just to go over to clean heating there, we would not be able actually to meet a reduction of CO2. In fact, the Department of Energy, fostered by a bill which went through the House of Congress in the United States, foresees by 2050 a reduction of 83% of greenhouse gas emissions related to cement and concrete production. There's no way to achieve that without new technology and innovation. So let's put this in the context of concrete innovation. Well, when you think about concrete, concrete has been used since Roman time, in essence. However, until the mid-80s, in essence, nothing happened. In fact, what happened was that the material, which is highly heterogeneous at multiple scale, became an industrial product. In the mid-80s, through breakthroughs in science discovering the sub-millimeter scale, people developing what they call high-performance concretes, which have a much higher strength, and I will say a little bit later on about this. In the mid-90s, people discovered the sub-micrometer scale, discovering there that the material is still heterogeneous but formed out of calcium silica hydrates in two fundamental forms, and that gave rise to materials, ultra-high performance materials, which today have a strength like mild steel. Well, right now we are discovering the atomic scale or electron scales, and I don't know what comes out of it, so let's call it secret for a moment. Now, what is the whole aim of bringing material into a green phase, a material like concrete, which clearly is not green? Well, the problem actually can be solved by increasing the strength of the material. And the problem is as old as Galileo Galilei, who once explained, why are there no monsters on Earth? The weight of a monster increases with its volume, the strength of body parts, bones, flesh, etc. increases with the section. So as the volume increases in weight, the section will not increase in the same way. That's why there are no monsters on Earth. You want to try this as an explanation for your kids when they're 5, 6 years old. It works. I tried it with my daughter. But we now can turn this around actually and say, okay, the CO2 impact is actually driven by volume. So if we increase the strength of the materials, we basically decrease the environmental impact by 1 over this strength increase. So if we increase the strength by 50%, by 100%, so double the strength, we have only half of the impact. So how can we achieve this? Well, we can't achieve that in the classical way as engineers used to work, in a bottom-up fashion, identifying a problem at a certain scale, solving it, going upwards. But actually what we have to do is we have to go down to fundamental scales. And that's maybe surprising that until recently, the molecular structure of the fundamental building block of concrete was not known. Well, recently we're looking at that here, a group of physicists, particular people from statistical physics, with material scientists and engineer, and actually find out that concrete at this fundamental atomic scales has much more in common with a glass than with what you would expect a concrete to look like, gray. A glass just delimited in its structure by water molecules which are in the interparticle space. Now, why is it so important if you look at that scale? Well, if you're able to change this molecular structure just a bit and increase the strength, you can propagate this up all the way to reduce the environmental footprint. And just to give you here an example, that's an atomic structure. You can tilt it, you can squeeze it, you can stretch it, and that's such a result here of such simulations, which basically shows you that if concrete were dry, we would immediately increase the strength by a factor 2, reducing by 50% the environmental footprint of this material most consumed on Earth. But that's just the atomic scale. So how do you bring this upwards actually to larger scales? The way how we do this is we take needles at nanometer scales and test the materials. What we're able to do then here, we're able to test some of those elementary building blocks and basically are able to identify how they look like. Well, that is not an Egyptian pyramid. This is such a rest of a footprint left after such a test. Now, what we're able to access in those materials is basically probability density plots of packing densities. So packing density is how you can pack granular materials. Interestingly enough, for the material the most used on Earth, it achieves in ordinary concrete a packing density of 64% as a dominating phase. Well, that's oranges randomly packed. So a little bit like these oranges which are here in this pot. But the second phase actually which comes into picture here is one which is 74%. It's the limit packing density of a spherical object in an ordered way. So this is, if you take 4 oranges, you put one in the middle, and now you get 70% in it. Well, these are 5 nanometer sized nanoparticles. There's no worker who puts 5 nanometer sized particles in there. Fascinating enough, this material is able to generate these type of behavior. Well, if we look what ordinary concrete can do, well, we all know the bad concrete constructions, and we also know that ordinary concrete has been and is currently still used as a means of oppression, like the wall, and here's another wall which remains to be seen fallen. Well, if you now look at ultra-high performance concrete materials which came out of the end of the 20th century, right after the fall of the wall, these ultra-high performance materials. You see here what you're able to generate. Well, you still have 74% packing density of those oranges, but now you even get another phase which fills in the space in between. You achieve 87%. So you can achieve actually higher packing in those bizarre materials. And that's the type of structure which you can create with it. Now, this type of behavior of oranges is not something related only for concrete, but in fact, this is sort of a stiffness behavior. That's the packing density of this here. These are concrete, 64%, 74%. Here in between are bones. So human bones, the idea that nature makes everything good is of course not true. It's just enough that we survive here. Up here, your ear bones, some other materials here, shales. It's a general pattern actually of these hydrated nanocomposites. Here an example of compacted clays from 3 kilometer depth, an important problem for natural gas formation in the US, Europe. And here an example of bone, the nanogranular nature of bone. So now you know what concrete and oranges have in common. Since I still have roughly 3 minutes time, let me take it just one step forward. From that scale up to the structures, because sustainable development has to do with employment creation, with elevating the stature. And if you have ever worked on a concrete job site, you know that concrete workers typically are the end of the food chain. So what actually can do materials to elevate their status? Well, I got involved in this project for the Federal Highway Administration to design a bridge for the future. A bridge which the newest material possible, but still feasible in the context, to replace actually 150,000 bridges of 450,000 of the US highway system. Well, the bridge I came up with, I'm not very creative in that here, is a classical bridge design, except for the dimension of it. When you look here at the dimension of it, that's 7.5 centimeters, something like that here. And on that bridge, you will have these heavy American trucks running. So they actually called me to Washington when they built it and asked me to stand below it when they drove over with the truck. That's evolutionary engineering, if you want. But more important about it, I went to the site actually where it was built. That was built actually in Kentucky. So the Federal Highway Administration asked me to collaborate with Kentucky. Now, Kentucky, for those who don't know it, for German speaking, I come from Bavaria, so I can say that. It's a little bit like Oberpfalz, you know. If you're able to build it in Kentucky, you can build it everywhere. In a positive sense, you know, I come from there, you know, so. Well, what you actually do there is you monitor the temperatures very, very carefully. Hydration is an exothermal reaction, but that's an old story, you all know that. But there's something about it. How can you tweak on the site a material to obtain this high packing density? Well, the story is easy. What this figure shows you is the temperature evolution inside the structure, inside this bridge over time. Interestingly enough, what actually happens is you start out with oranges in this disordered organization. You apply some heat, actually from its exothermic sources, and the structure falls in place as this high strength structure. Importantly enough here is when I came to this job site and worked there, and these were Hispanic workers in Kentucky, believe me, everybody had the feeling to be part of something more important than the work itself. And that shows you how materials which can have an environmental impact have also enormous social impact. To conclude, what's the matter with green concrete? Well, concrete is not green, we all know that, but it's no secret. There's a cultural meaning to it, and actually the cultural meaning at that point is the fusion of physics and engineering to solve the next problem of environmental footprint. But solving the environmental footprint with a view of the 20th century, which is just, let's get it out, just have the same type of idea of just solving the problem. Without putting this in the larger cultural context, I'm afraid we will not be sustainable for the future. And this is just a reminder that there are not only oranges on this world, but also other fruits. Thank you very much.